The conventional 60 SRAM has been the traditional choice for the implementation of embedded memories due to its high access speed and refresh-free static data retention. However, the 60 SRAM has several drawbacks in modern systems, including its large transistor count that occupies more area, two-port operation is not supported in 60 SRAM, and also it has static leakage currents from VDD to ground, which causes high static power consumption. Thus, conventional GC-eDRAM becomes the replacement for SRAM as cache memory in microprocessor-based systems due to its several advantages. However, there are also some problems found in GC-eDRAM. First, GC-eDRAM has high power consumption due to its dynamic storage mechanism that requires periodic and power-consuming refresh cycles. Besides that, it has short data retention time because of the leakage currents and small in self-storage capacitance that result in faster data degradation. Therefore, low-power design method, which is single supply 3T GC-eDRAM, is proposed to overcome the limitations. For this proposed gain cell, a transmission gate is used in the right port instead of a MOS transistor. Transmission gate able to pass full swing level to the storage node even without boosted voltage. With this, the GC-eDRAM able to provide strong initial logic level which reduce the data degradation in storage node and resulting in higher DRT. Thus, power consumption is reduced by reducing the power-hungry refresh cycles to maintain the data. A 4 KB memory array architecture based on the proposed gain cell is implemented using 130nm standard CMOS technology. The proposed cell exhibits several advantages as compared with the conventional GC-eDRAM and SRAMs. The proposed single supply 3T GC has high storage density with 99.6% yield availability. With its low-power design technique, it achieves prolonged DRT that helps in reducing data degradation rate in the storage node and consequently leads to lower power consumption. Lastly, it has smaller cell area than SRAM, thus the proposed single supply 3T GC-eDRAM is suitable to be implemented as cache memory in ultra-low power systems. As we can see that the total power consumption of embedded memories will reach almost half of the total power consumed by the processors for the next 15 years. Therefore, reducing power consumption is one of the most important aspects of embedded memory designs. So the target segment and impact of the proposed low-power design of GC-eDRAM would be to offer the engineers an alternative design to be used in cache memory to achieve lower power consumption. Next, I will move on to the project demonstration. In my project, 4 KB memory array were built based on the low-power design GC-eDRAM. First, I will show the memory array architecture implemented using single supply 3T GC-eDRAM. So this is the schematic of the 4 KB memory array that is connected with all the functional blocks in the right port and in the red port. And after zooming in closely, you can see that this is the single supply 3T GC bit cell, and this is the topology of the single supply 3T GC. After that, this is the layout of the memory array architecture created based on this single supply 3T GC bit cell. Next, this is the test bench to run the simulation. Before I start the simulation, all the settings were adjusted and the extracted parasitic netlist is included. Now I will run the simulation. After the simulation process is done, we can analyze the performance of the memory cell. We can see the output waveforms for the operations, and this is the output waveforms for write operation, where a logic level 1 is stored in the storage node, and this is the output waveform for read operation, and the data stored in the storage node can be successfully read out. Lastly, this is the data degradation curve in storage node that is used to determine the data retention time. This is the curve obtained from the TT, typical process corner analysis, while this is the curve obtained from the FF fast corner analysis. We can see from the slope of the curve for TT, typical process corner analysis, is not very steep, which indicates the slow data degradation rate.